Okay, so what is entropy and what do we have to define it as? Entropy is defined as the number of arrangements you have and the energy in a given system. The specific definition that you should memorize is the one that's in the current learning objectives. And so that one is, because I copied them over, the number of possible arrangements of the particles is pretty much the same, and their energy in a given system. What's a system again? The system is whatever we are, what we are studying. So generally speaking, in chemistry, it's the specific reaction that's taking place. So it's whatever we're studying, whatever reaction is taking place, we define that as the system. And so the main idea here that you should get as we're going through examples is as we increase the randomness of a system, of an area that we're studying, we're going to increase entropy because you have a higher probability for whatever you have to be in different configurations is the idea. And so system is whatever is the part of the universe that's under investigation. For us, it's a chemical reaction, right? And then the surroundings is everything else that isn't the system. So this is a highly ordered system. You increase the entropy and it becomes more disordered. I think the sandcastle, I like to show it because I think it's a good example of showing that the sandcastle is very ordered. And then when all the sand spreads about, that's very disordered is a way to understand it in comparison. What? Okay, so this leads us into something called spontaneous reactions and spontaneous things that happen. And so the first type of question you're going to have in your homework is to predict whether something happens on its own or whether it doesn't happen on its own. A spontaneous change is defined as one that does happen on its own, although, I'm going to add an addendum here, although an input of energy, an initial input of energy, what's that called? May be necessary. Something called, kick-starting the reaction, the activation energy. You may need enough energy to get it out off of the hill, but then the reaction does proceed. An example of this that would be a little dangerous. If we have a flammable substance, right, like methanol, we know that it will ignite, that it will light on fire, but you need a spark for it to light on fire. That still we know will happen as long as you got that spark there. That's going to happen spontaneously. And that's why some materials are so dangerous to have around. Magnesium reacting with HCl, I would call that spontaneous. If you'll recall what happens there, you throw a little bit of magnesium wire into HCl, what happens? Do you remember? It fizzes, it bubbles, it releases what? It releases H2, right? H2 gas comes out. You've got Mg2 plus and Cl minus now in your solution. And if I were to take a lit wood splint to it, I had done it in a test tube, it would boop, just like that, right? It would sound like that. All right, most double replacement reactions, if you form a precipitate, they're going to be instantaneous. They happen on their own. All you got to do is mix them together. They form a PPT. It happens. Methane gas reacting with oxygen and light. This is the same idea. You may need a spark, but other than that, it is going to spontaneously combust. Something of note here, spontaneous reactions, just because something is defined as a spontaneous reaction does not mean that it happens fast. So that word spontaneous, that can lead you to an incorrect assumption, because when we think of spontaneity, we think of, fast, somebody who's doing something instantly. And so when we say spontaneous in chemistry, we're just saying this does happen pretty much on its own. Does not need to happen quickly. So it could be something that happens over weeks, months, years. An example I can think of is magnesium in cold water. If we place magnesium into cold water and we come back to it months later, it will have reacted. It's just such a slow reaction, you can't really tell when you're looking at it that it's happening. Yes.
What wouldn't be as
What wouldn't be? I would say thermal decomposition. The reason why thermal decomposition is not spontaneous is because as soon as you take the heat away, it will no longer happen. So it doesn't just require a spark, it requires a high amount of energy for it to continually go on. But if you change the energy you can make a reaction go from non-spontaneous to spontaneous. With enough energy, you can make it happen. So spontaneous basically addresses, does this happen? Literally in the simplest terms, spontaneous is, does this happen? Will this happen? What will never happen, that I don't think, is if I put a diamond in water, it will not decompose. Just won't happen. We would call that a non-spontaneous process. Does that make sense? So another way I think spontaneous is, does it even happen? Does it happen, bro? Or does it not? If it happens, it's spontaneous. Most reactions we study are spontaneous because otherwise our life would be very boring. The study of chemistry would be extremely boring if nothing actually happens. So everything that we study for the most part is usually, spontaneous. Because why bother otherwise? Go back to why bother, bro, if it doesn't happen. All right, so let's talk about a little bit more of entropy. I believe this diagram or something similar to it is in the textbook. If we were to take a system and we were to expand its volume. So if you see here, this is a little lever. On this side, you have all the gas molecules are on this side. But when you open the lever, the gas molecules separate to both sides. Which of these do you think has higher entropy? Higher entropy, because you have your gas particles spread over a greater area. So the lower the volume, the greater the pressure, the less the entropy, right? So lower volume, greater pressure, lower entropy. If we were to increase the volume, we have more arrangements that can occur. That's the idea. And so higher entropy will occur at a greater volume, lower pressure, like that. And so the process of diffusion is a process of entropy. If you were to have perfume and you open it, over time, you're going to smell it over a large distance. If you leave that container open, what is that indicating? Whatever particles are evaporating out and they're spreading, and your nose senses them. All right, so checkup 1. Which reactions are likely to be spontaneous, meaning does it happen? First one, sugar, does it dissolve in water? Is that a relatively easy process? Will that happen? Spontaneous. Now, what wouldn't be spontaneous on the other notes? Silver chloride dissolves completely in water.
How much more?
Unless you had, what was it? We did a calculation a couple of weeks ago, 1.14 times 10 to the 14th decimeters cubed of water. Let's say we had 10 grams in 1 decimeter cubed of HCl. Is that going to all dissolve? No. The smell from an open bottle of aqueous ammonia diffusing throughout the room. Oh no. I have to have ammonia today for the lab exam. So would that be spontaneous or non-spontaneous? It's 100% spontaneous because I can tell you that you'll be able to smell it.
I smell it from here.
The walls, I guess that little tiny space, it depends on the concentration of the ammonia, to be clear. It won't be that concentrated. Water turning to ice at 10 degrees Celsius. Ramon?
Non-spontaneous.
Non-spontaneous, because that doesn't happen until 0 degrees Celsius. The kinetic energy is too high for that to happen. So that's non-spontaneous. Basically, again, does it happen or not? This is not going to happen. Obviously, you could change things like pressure to affect it. Like that, it could happen at that temperature, but we're talking with everything else constant. So STP, just the one thing that we're changing. Everything else stays constant. Ethanol vaporizing at 20 degrees Celsius. The boiling point is 20 degrees Celsius. They had to give you that information. So will that happen?
Yeah.
Yes, spontaneous. It is at its boiling point. Water mixing completely 100% with oil. That's non-spontaneous. Not happening. I mean, you can vigorously mix them, but the moment you stop, what ends up happening? They separate again, right?
Is it possible for them to like combine at all?
If you add an emulsifier, that's a chemical compound that can like cause them to combine. They're called emulsifiers. That's how you get like specific types of food products that you have fats, but they're mixed with aqueous is emulsifiers.
I was just gonna say that.
Water mixing completely, we did that. Calcium carbonate decomposing at room temperature. So CaCO3 decomposing at this temperature, no spark. So non-spontaneous. Notice if we said that we applied a flame to it, like a Bunsen burner, and we raised it to, I don't know, 700 degrees Celsius, it would decompose. Can't get it out of my head now. All right, so are we good with this initial idea of what entropy is? So comparing entropy values. Do you remember delta HF? You remember that thing? Do you remember when it was 0? All elements in there, standard state. Well, it turns out that for entropy values, nothing is 0. In standard entropy values for any substance that exists, there is nothing that has an entropy of 0 at room temperature. Why?
Like, what if you had a single molecule of silicon in a vacuum?
Vacuum wouldn't be standard conditions. I think that does cover that, I believe. But we're talking about all elements at their standard temperatures and pressures, right? They do not have an entropy of 0. Why not? Go ahead, Ansel. That means there'd be no possible different arrangements. And even if we're in the solid phase, can molecules vibrate? Is vibration still considered a movement of sorts? So although a solid would be a very low entropy, it does have some entropy. So in order to use entropy values for calculations, you do not have to memorize entropy values. Yay, great news. Because they'd have to be given to you in a table or you'd have to be solving for one. You have to consider that you're working with a standard pressure, that you're working with a standard temperature, and every substance that is given to you is given in its standard state. So standard entropy values are written as S with a little circle. This little circle here means standard conditions. If you are to read any advanced science, biochemistry, physical chemistry, advanced text, you will see the S with the circle, or you'll see a G with the circle, and that means we're in standard conditions. You're going to see that throughout this year because when we get to electrochemistry next unit, you're going to see E with a circle, and that means something else that's not energy. E stands for
Electricity.
kind of. Go ahead. It stands for voltage
Oh,
of a system. Go ahead.
what if we have 0 condense?
I'm sorry?
If we have 0 condense, wouldn't that be 0?
Did you say what? Carbon?
No, if we have 0 Kelvin.
Oh, but that's not standard conditions. So once again, that standard conditions means we are operating in room temp, like close to room temperature, which you would experience in a laboratory, standard laboratory conditions. Obviously, you can alter the conditions, and physicists love to do that. Physicists love to play with conditions so that they can, you know, approach the realms of what is possible as they try to learn more about quantum mechanics. That's what physicists do. We're just studying, because it's chemistry, the realm of what is material that we know naturally exists. That's really the difference between the two classes, if that makes sense. All right, but sometimes, you know, physics enters into discussion, and this is one of those areas where, you know, physics enters into discussion. All right, so our entropy units, be aware of these. It's joule, Kelvin, moles. Joules over Kelvin times moles. Joules is regular unit of energy. Kelvin is temperature, right? And moles means we depend on amount, meaning anytime moles enters the discussion, could we change the amount of moles and change the amount of entropy? Totally, right? All right, so let's take a look at some entropy values. These are given to you, and see if we can make some comparisons. First, entropy values are always positive. Why? Why are entropy values always positive and never negative? Why?
I was gonna say because stuff has energy and
All substances have some movement at room temperature, right? Have some movement at standard temperature. I'm going to call it STP because I don't want to keep saying standard temperature and pressure. And that's what we call standard temperature and pressure in chemistry. We call it STP. So all substances have some movement. Look at some comparisons here. Carbon dioxide, 213.6 joules Kelvin mole. Ammonia, 192.3. Water, 69.9. Diamond, 2.4. Look at how low diamond is. Why? Super strong carbon bonds, very little disorder in a diamond. Yes. Yes. About the lowest disorder an actual material at room temperature can have. Yes.
So how do you measure entropy?
It's the different probability of the movements. It's most of those calculations are derived calculations, but you can look it up. What other generalizations can we make from this sample data? Gases entropy value versus liquids entropy value. I'm assuming you can find the entropy value. Typically, you probably use your enthalpy value as one of your things. You have to know the other equations that we learn on Friday, but I'm pretty sure you can use that information to derive entropy values. What other generalizations can we make from the sample data? Gases versus liquids. What do we think? Gases generally have higher entropy or liquids? Gases have higher entropy. Liquids entropy versus solids entropy. Liquids have higher entropy, right? Here's an interesting one. Simple substances versus more complex substances. I think it's hard to compare here because you don't really have enough compounds to make the comparison. Let me see if it's better to see over here on this chart.
Yeah.
Let's see. Look at water liquid versus H2O2 liquid. There's a comparison. They're in the same phase. What we mean by more complex is more atoms. Which one has higher entropy? And that is more complex, actually. So more complex substances, because they are more complex, they have more arrangements that they could have. Like there's more movement around the bonds that they can have. Therefore, more complex is actually more entropy.
Does MgO have more? Isn't it more complex than Mg?
I think because they're different, like this is a metallic bond and this is an ionic bond, there's something else going on there. Like generally speaking, you have to make even comparisons. That's why I compared two that are in the same phase and the same type of bonding. So if I'm comparing same phase, same type of bonding, then I look at complexity of substance. Otherwise, you have to go into the different types of forces of attraction, which would influence the, you know, here you have the delocalized electron moving through a lattice. So that's movement itself. Whereas this is a lattice, ionic lattice, which doesn't have that free movement of electrons. So that could be a factor. Yes, go ahead, Caesar.
Well, why is oxygen so high?
Because it's gas.
Well, it's, yeah.
So it's higher than.
These are generalities. And these generalities are brought up in the book. You can't really, you need exact numbers if you're actually going to do calculations. So generally more complex substances though, and this is generally true, more complex substances have higher entropy. If all other factors are held constant. And so moving into, we're almost to the math. But first of all, we still have to discuss a little bit more of what increases entropy. And I think that some of it's pretty straightforward, at least what you need to know for Cambridge is pretty straightforward. If we increase the movement of particles, would that increase entropy? Absolutely. This is going to have the least entropy, the solid phase for any substance, and comparing the same substance, the gas would have the most entropy. So if I add energy, I increase entropy as a result. Adding energy increases the entropy of a system. And so the idea is that if there's more disorder, there will be more entropy. So you can always look at a phase change and see if there's more energy being added and the phase change is going to a more disordered phase. This means you have more entropy. So gases always have the highest entropy. So can we explain the difference in each of these? Br2 liquid versus I2 solid. Why is this substance, why does it have a higher entropy? And this is, again, a textbook question. Looking at checkup 2. Why is this the higher number? Because we're comparing Br2 is in liquid state, whereas I2 is a solid. So comparing the states of matter is the reason why. The second one, H2 gas versus CH4 gas. These are established values. CH4 gas is higher. Why, Ramon?
Because CH4 is more complex.
So more complex. CH4 gas, they have the same type of intermolecular force. Everything else is constant. They're in the same phase. They're both gas phase. So if all other things are held constant, we're looking at the complexity. And here CH4 is a more complex molecule, which basically just means that in CH4, you have more movement in the rotation around the single bond. So basically there's more movement like that. Whereas H2 only has this. Yes.
If time is like really big, right? It's
Yeah.
then why is it not complex at all? Why is the
Because it's in the solid phase and it's got really strong covalent bonds which inhibit its movement.
Because those really, really strong covalent bonds are very difficult to break. So it's not really moving out of the solid phase. That's diamond is actually a very special molecule that has very special properties. You all studied diamond last year. Didn't you? No? In AS Chem. It's giant molecular. Because of its giant molecular structure, it gives it an extremely low entropy, is why. Hg liquid versus Na solid. Hg liquid is higher. Why? So Hg is liquid, whereas Na is solid. we could increase the entropy of sodium real quick by throwing it in some water. But not in its current state. SO2 gas versus SO3 liquid. SO2 gas. So even though it's less complex, yes, but it's in the gas phase. So be careful for that. So SO2 gas is higher because gas phase. All right, so that is some of the general ideas you need to have about entropy, just the general how this works in the first place. So we're about to get to our signs and we're about to get to our math for the rest of class. I think the math here is not awful. Personally, you'll tell me if you agree or disagree. It's the same as the delta. Do you remember calculating delta HFs back in AS Chem where you did products minus reactants? Same ideas are going to be at play here. And you're actually going to be calculating delta HFs again next class. I know you're so excited for that because we need delta HFs for the finding the energy of that's available in a chemical reaction. We need that. So here we go. Entropy changes in chemical reactions. We can predict if a reaction will end up with higher entropy or lower entropy by looking at the phases of our reactants and our products in a chemical reaction. So if we start with something more ordered and end up with something less ordered, that means that entropy increases. And so remembering that entropy is S. If delta S, which we define as products minus reactants, is positive, what this means is that the entropy of my products is greater than the entropy of my reactants. And so if the entropy of my products is greater, what that means is I have increased entropy. So a positive sign, and this is where it said signs are going to become relevant and important. Cambridge will also ask you to predict signs of reactions. So a positive entropy means that you have a reaction that's resulting in more disorder at the end of that reaction. The products have more entropy. And so if delta S is negative, this can only happen because remember your S values are positive. Thankfully, your S values, your entropy values are all positive. So we don't have that issue with last class where we have subtracting negatives, minus, minus, minus going on. Confusing. Here, all your values given to you will be positive. So if my products have less entropy than my reactants, that means that the negative sign is greater, right? So you would have a negative delta S. And what does that mean if I have a negative delta S? You'll have less disorder or more order, right? At the end of this chemical reaction, you end up with more order. What do you think nature favors? Disorder. So when we get to Friday's lesson, we're going to see that this is actually just one of the factors in play, whether a reaction will take place or not. It both depends on your entropy and your enthalpy of your system to tell you if a reaction will take place. All right, so nature favors more disorder, positive entropy. But that doesn't mean that a reaction won't happen on its own. There's more involved. Let's take a look at a few reactions and suggest whether the entropy of the reactants or the products will be greater or whether it's difficult to decide. Explain your answers. So let's do this by saying either our delta S will be positive or our delta S will be negative or we're not sure. First one. Go ahead. Yes.
Why does nature favor?
Because of the second law of thermodynamics. The entropy always increases because we are not at equilibrium. And so all the established, like what happens if it happens or not, we can experimentally prove whether or not the actual reaction happens. And this is the theory that backs it up. All right, so first one, A. When I go from NH3 and HCl to NH4Cl, they start as gases and it ends as a solid. Is this an increase in entropy or a decrease in entropy? It is 100% a decrease in entropy. And the way that that would be communicated to you is delta S equals Negative. Does that make sense? Second one. You have a liquid and a gas turning into just gas. Do you think entropy increases or decreases? Remember, there is an option. Is it difficult to decide? What are the factors at play? You're going to something more complex. That's a gas. Here you have a liquid turning into a gas, right? But so the moles of gas are the same on both sides, but here it's a little bit more complex. So I would say there might be a slight increase in entropy here, or difficult to decide. One of those two is true. So you can either say difficult to decide, and the reason why is because you've got the same amount of moles of gas on each side, or you can say maybe slight increase in entropy. Watch the wording that they give you. If they give you the option to say that, then yes. If they don't, then no, is the way that I would approach it. Usually they don't. And usually they give you something that's more apparent to be able to predict. Yes.
We also never say maybe, like,
No. This is not an actual Cambridge question. This is just a reasoning question. So no, that wouldn't be the appropriate way to say it. But it could have a slight increase in entropy because it's difficult to decide. That probably wouldn't actually show up on a Cambridge exam. All right, next question, C. You've got a solid and a gas going to just solids. What do you think? Definite decrease in entropy. Because no gases, all solids. So here delta S equals negative for sure. And here, solid and gas go to solid. Another decrease in entropy. Delta S equals negative. So let's look on the next slide for an actual Cambridge question. So here's an old paper 4 question. Here they say what to do if there is no entropy change. They say for each reaction, predict the sign of the entropy change. If you had something that would be no entropy change or difficult to decide, go and write no change in the table is what they're telling you to write. First one has been done for you. They tell you CO gas plus O2 gas goes to CO2 gas. Why is this negative, by the way? So the idea is that you're going from more moles of gas to less moles of gas. I remember in my chemistry classes, what we would do is we would count the moles of gas on each side and subtract them. And that's how we would get the signs. So here that would be, if we wanted to do it that way, it would be delta S is 1 minus 2. 1 mole gas for the product minus 2 moles gas for the reactant. And what's 1 minus 2? Negative 1. That's how we would do it in my classes. The second one, what do you think? Also negative. Because you go from having a half a mole of gas here to no gas. Therefore, more order, sign of delta S is also negative. And if you just wanted to math it out, you would do 0 for your products and 1/2 for your reactants. It's products minus reactants. So you would do 0 minus 1/2, which is negative 1/2. Negative. Kind of make sense? The next one. There's no gas involved. Can we make a prediction though? It's also negative because everything is going to a more condensed phase. Solids have much less order. They're donuts with that. That's what they were so long. Yeah, I didn't think it would be that long. And then the last one here. Solid and aqueous to aqueous, gas, and liquid. Definite increase in entropy. And so we would say here the sign is positive. Yes.
Out of curiosity, if you were to put increase or decrease, would you lose the mark?
You would lose the mark. If you put increase or decrease here, you would lose the mark, even though you are not giving an incorrect idea. You're not giving the sign, right? So increase is not a sign. So you have to say whether it's negative or positive. Yes, Atzel.
What is aqueous? Is it like in between, like?
Aqueous is if I have it in water, it's moving around. That is a pretty disordered state, to be fair, because things that are in water are moving around a lot. That's why we say in equilibrium, we only count aqueous and gases because they are moving states. But gas is moving the most. And here you both have aqueous. These kind of cancel each other out. So really, you're just looking at, oh, that goes to that.
So when you say aqueous,
It's more movement than liquid, is that what I would say, because it breaks up the regular liquid phase. Aqueous is one of your more moving states, but not as much as gas. Yes.
What was the explanation for the third one? Like, why was that?
Because you're going from a solid and a liquid, and it's a phase change to just a solid. And liquid is always more disordered, like significantly more disordered than a solid. So even though it's a more complex solid, it's still just a solid at that point. Everything's like stuck together in the solid phase, just vibrating, no movement. Yes? All right. Why? The entropy change for the first process, why is that negative? What's the way that they want us to respond to that? The products have less moles of gas. That's literally the way you correspond is you count the amount of moles of gas on each side. The products have less moles of gas. That's how they would award the mark. So if gases are involved, you literally just count the moles of gas to get your answer. Which side has more moles, which side has less moles, and that gives you the answer. All right, I think we're ready to get to numbers almost. The number work is not that hard here. It's good news, yes. CO2 is more complex slightly, but there's two of these still. So that effect is not nearly as much as the difference in the amount of gases, yes. All right, I wanted to include this question. I think something like this shows up in the textbook, first of all, and it is somewhat common to show up. You love graphing questions, don't you? Entropy is a measure of disorder. Assume the entropy for water is 0 at 0 Kelvin. So 0. Could you sketch a graph to show how the entropy changes for water between 0 and 300 Kelvin? Is it a linear change or not? Let's think about it. How would the entropy change for water? Would you first have to figure out its melting point, perhaps, and its boiling point to find its phase changes? What's the melting point of water? Is that something that Cambridge assumes that you know? It's 0 degrees Celsius if you didn't know. And what would the boiling point of water be?
100 degrees Celsius?
Yes, that's what the Celsius scale is based off of. Yes, I know that. But do you have that memorized? Do you have the boiling point of water in Kelvin memorized?
Not me.
I would think most people have it. If they have it in Celsius or in Fahrenheit. Fahrenheit, we pretend doesn't exist in this class. So we're using Celsius, which is actually based off of the melting point and boiling point of water. That's where 0 and 100 are set. So 0 degrees Celsius would be what temperature in Kelvin? Negative 273 Kelvin exists?
No, never mind.
The opposite way, right? 273 Kelvin. 273 Kelvin, right? So then, how would this sketch graph work? Does entropy increase with increase in temperature? What do we think? If I increase the temperature, I'm adding energy. Energy starts more vibrational movement, right? So although they're not changing phase, they're like, right? Until you get to what temperature? 273. So I would put like 273 like that. Make a little mark for yourself. So increase, 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 increase. Do the exact numbers matter? They don't give a single value here. They're just saying, tell us it's a general increase. And then what happens at 273? Because you've changed the phase of matter from liquid, from solid to liquid. And then you still have a increase from there. Because as you go through the liquid phase, now it's going faster and faster and faster again. Yes.
It should be like you kind of write it a little bit shaky.
I think you don't have to do that. No. Just the general, and then it goes. Yes.
So you are supposed to know the on boiling point water.
Yes. Yes, you should. And I would actually say to be a little bit more specific. Let me hold on.
Oh.
I would even do it like this, like that, even more. You know what I'm saying? You should. Because there should be a big jump at the melting point. And where else would there be a big jump? At the boiling point. Now, boiling point is mentioned here, so we don't care. Just the big jump at the melting point and then continual increase from there. That's how you earn the marks here. 2 marks. 1 for recognizing that the big change happens at 273 and 1 for the general increase is how they do the marks here. All right, so next, time to do the math. This is the formula. The change in entropy of a system, and you only have to calculate the system, is the entropy values of the products minus the entropy values of the reactants. Stoichiometry matters, amounts matter. And when looking up your standard enthalpy values, make sure to use a reference for the correct state of matter. If you were to look up entropy values and you look them up online, make sure you're checking whether it's a solid, a liquid, or a gas. For example, H2O solid has a different entropy value than liquid, which has a different entropy value than gas, and temperature affects the entropy values. So be careful when you're looking up values. In the lesson, I put a bunch of reference entropy values. Those should be used for your homework, just so you're aware. Use the standard reference entropy values for your homework. Here they are. These values, don't lose your handout, like I said, because this is going to be the values that you use for not only our lesson today, but also for the homework. Use these to help you with the calculations. Here we go. 4A and 4B. The question for all of these is to calculate the standard enthalpy change. Calculate delta S for the system. So, what will we do for this one? What should we do first? 1, find entropy values. 1, find entropy values. Make sure you consider amounts, right? Because the entropy values are joules per mole. So if you've got 2 moles, what would you have to do? Right. Consider amounts. And then it's use formula. And our formula is delta S equals, and it's actually more complicated than this. It's the addition, the summation sign, the addition of your products minus the addition of your reactants. This is how it's written in the Cambridge Standard. Remember, summation just means you add up all your products and you add up all your reactants. You can scan, show, and go, yes. So then how we pick our numbers up? Chart, right? H2O2, 109.6. That's that's joules per mole. But how many moles do we have? So it's gonna be 109.6 for this one. But what would we have to remember to do? Multiply by 2, which I need my calculator here. I get 219.2. And then what about my products? I always like to put a line here. What is my water liquid number? Notice there's water liquid. Go ahead. And steam. Be careful. Don't choose the wrong value. Look for the state of matter. Which number do I need here? 69.9. Multiply by 2. And I get 139.8. And what about oxygen? I think that one is 205. We saw it earlier.
Yep.
205. Do I need to multiply that by anything? So how do I plug this in the formula now? I've got my entropy values. I've considered my amounts. I need to use my formula. What should I do?
The products are the reactants.
It's the reactants from the products. So first you should combine your products together because it's the sum of your products. So the sum of my products is 344.8. So it would then be 344.8 minus 219.2. Double check me because I didn't do the math on my own earlier, but it should just be 125.6 positive.
So that's why if you just have H2O2 just sitting around and become H2O and O2 because it goes to this.
It increases entropy. Yeah. That's part of the explanation. There's an entropy factor in there. But remember, there are 2 factors. So there's also an enthalpy factor we're looking at on Friday. And that gives you the spontaneity of an actual reaction, which is what we call delta G, which we'll be learning about on Friday. That's why I said Friday's lesson is really important because it kind of brings everything together to determine whether or not a chemical reaction is indeed going to happen or not. We can figure it out at any temperature. Okay, positive 125.6, what's the units? Joules per mole times Kelvin, or joule, mole minus 1, K minus 1, right? So that's the answer for this first one, 125.6.
Isn't that how we want a high delta S but a low delta G?
You want a large negative delta G for a reaction. That's where we're going to get to. Delta S, you would want it to be positive entropy, a high positive entropy, yes, for a reaction to happen, yes. That is part of next class's lesson. All right, second one, do the math. What do we got? NH4NO3, that number is 151.1. N2O gas, 219.7. 2 steams. What steam? 188.8. Be careful again when picking your numbers up that you choose the right one. I'm talking about your homework. Mistakes get made here. And so that's not a negative. That's just. So this is, I have my products, 219.7. You notice I always put a dividing line between my reactants and my products. I get 597.3. Please check my math that I've entered everything in the calculator correctly. And then what should I do once I've got my total for my reactants and my total for my products? Subtract products minus reactants, right? So 597.3 minus 151.1. I get 446.2. And that's also joule mole minus 1, K minus 1. Quick question before moving forward. Do these answers make sense? Does it make sense that the first reaction gives you positive entropy? Luke mentioned that one. Does it make sense that the second one also gives you positive an amount of entropy? For sure, because you're going from solid to gas. That's a high amount of entropy change. Lots of entropy change. All right, we're actually 2 questions from being done. We may have time for a little quick activity at the end. Gym kit. I loaded a quick gym kit just to have something for like the last 10 minutes of class. So if we get through this, we'll do a quick gym kit on entropy. So 2mg plus O2 goes to 2mgO. What do we got to do? Get the numbers, right? Do we consider the amounts? So this would be 32.70 multiplied by what? 2 plus 205. That's me remembering off the top of my head what that was. MgO, 26.9. But should we leave it at 26.9? No, we should multiply it by 2 again. And then we got to do the math. Do you remember the style of math from ASCAM when we did it for delta H? $270.4, 2 times 26.9 is 53.8. Which way do I subtract? Products minus reactants. So delta S equals 53.8 minus 270.4. And let's see, does that make sense? Negative 216.6 joules mole minus 1, K minus 1. Does that answer make sense with the concept? Hi, welcome back. That took a very long time.
Yeah.
Thankfully, we recorded. All right, last one. 2 sodiums. How about this last one? You all try. I'll check it. You try this one. Raise your hand and I'll tell you if it's right or not when I come by. I'll sign off on it instead of giving a stamp because I don't have my stamps today. Let me just get the numbers myself so that I know what number answer I'm looking for. Yeah, we're on the very last slide of the lesson. Yes.
Is it gonna be up today?
It'll be up either today or tomorrow. It'll be up before the teacher planning day. Because all the lessons have to be transferred into YouTube and uploaded. So it's a little bit of a process. So it'll either be today or tomorrow. I can't guarantee today, but tomorrow after school, before the teacher planning day.
Okay.
All right, I'm gonna check for a few answers now. Let me see.
Is this it? Sure.
2 times 50 is not 250.
Okay.
Oh, that's good.
Vermont? Yes. 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 Got it.
Let's see.